So in our last video, we introduced two very common iteration orders for traversing over a graph, DFS and BFS, and we hinted at we're going to use those as building blocks to solve many problems or many algorithms that will run on a graph itself. So for example, that first one we introduced kind of earlier in this lecture, this ST connectivity problem, we can use BFS as a really great building block, something to start from. So here I've actually shown all of the code for BFS, except I've changed the name to ST connectivity, or a short version, so it fits on the slide. I've added a new parameter for the target. And then in our iteration, whenever we find our target, we could return true. And if we make it all the way through for all going layer by layer from our start, and we never find the target, then we know that they're not connected, that there's no path from the start to the target, so we could return false at the very end of the while loop. Notice in this algorithm, we actually don't care about any of the particular properties of BFS, so we just needed some traversal, so it would have also been fine to use a stack here instead of and use DFS. So either would have worked, we just needed some traversal, and we just needed to return true whenever we found our target. Okay? So that's how we can use BFS or DFS as a building block. ST connectivity, just one of the searches with an extra if statement on top of it. So let's try explore another problem, one that we'll call the shortest paths problem, or in particular, what we're going to call the unweighted shortest path problem. So given a vertex S and a target vertex T, how long is the shortest path from S to T? What edges might make up that path? And so what we're going to say here is it's an unweighted case. We're not going to worry about edge labels. We're just going to count the number of edges from S to T in this path. So notice this is a slightly harder problem in some sense. One, because we want the shortest path, and we have to actually tell as the answer, what is the path? We don't just have to say, oh yes, they're connected or not. So this is going to be a little bit harder, but still totally doable. We just need a way of keeping track of how far each node is away from the start. And it sounds like that's a job for breadth first search, where we keep track of some extra information. So this is a lot, but let's explain it. This is still breadth first search. Just go through the tree, or sorry, go through the graph, but we're going to keep track of some extra things. The first thing we're going to keep track of is some extra maps to help us store information about each node. We usually think about these algorithms that need to keep track of extra information is just using extra data structures, like that set of visited nodes. A totally other valid approach is to change your graph data type, like the vertex class, to have this extra information stored at each node. That's a bit of a design decision of how much do you want to put in the node versus just keep track externally. So one thing we're going to keep track of is this edge to map, which is keeping track of what edge we take to get to a particular node. So for any node, what edge do we take to get there? And then we're also going to keep track of this map to keep track of the distance. Just what is the number of edges to take here? And notice, because we're using this unweighted shortest path case, we can simplify things quite a bit because we don't care about like any labels or anything like that. We just care about what's the number of edges we've taken to get here. And so we can start off by initializing this thing for our start node, maybe just set the edge to get there to null because it's just some value that we don't actually care about. Same thing for distance. Now, distance could be 0 because the node is 0 distance from itself. Now the code is exactly the same for the rest of this, except when we get to this part where we're finding a new node. And in that case, if we find that new node, we're going to add to our edge to map some new information saying, oh, okay, to get to this new node, take this edge from me to this next node and set its distance to be 1 plus my distance from the start. Now this is a bit hard to reason about without a picture, so let's go through an example. We're going to use this extra information to keep track about state in our graph traversal. So we start with A, we add it to our visited set. We also have this dist2 map. We're going to say, since it's our starting node, we're going to set that to 0. Now we're going to remove that and add all of its neighbors. And for each neighbor, we do this step where we say put edge to edge. So we're going to associate which node we're going to. We're going to node B with the edge that we took to get there. So we can remember how we got to B. The way I reference this in this picture is this red arrow. We sometimes call these back references. Notice, a very important thing. This is not part of the graph. It's not adding like a new edge that's from C to A. It's not taking this undirected graph and turning it into a directed one. This is just me trying to overlay the extra information I'm storing in these maps. So in these maps, I'm trying to show here that for node B, I'm associating the edge here that took us from A to B. That's kind of this extra information I'm storing right now. Whoops. And then I store into the distance put map the current distance from the place we came from, 0, plus 1, because we just took an edge to get here. So I'm going to store 1 for each. Okay, so then I just go back, add it to my visited set, go to the top, remove the next node, which in this case was B. That's going to add D, and the edge to get there was the one we just took from B to D. And then the distance to D becomes 2, because it's the distance to B plus 1. Then we explore all of C's neighbors that we haven't visited yet. E becomes a distance 2 away, and we associate this edge we just took so we can get back here. So, and then we explore the whole tree. So notice one thing I actually still haven't answered: how do we actually find the shortest path? But all this extra information lets us reconstruct the answer. So all of this external information, again, I want to highlight that these red arrows and the blue numbers and the green visited set, none of those are on the graph necessarily. Like, we aren't changing our graph structure. We're just using them, storing this extra information, maps or sets or whatever, to keep track of these things. Now, what about that target vertex? How do I find the shortest path from one point to another? Because I didn't quite answer that. Well, what we've kind of done, and by exploring this whole tree, or sorry, this whole graph, is in some sense we've answered this question for every node. So instead of calculating the shortest path from the start to the target, we've calculated the shortest path from the start to every other vertex in the graph. We call this thing a shortest path tree. It's a tree that defines what are the subset of edges that we take to get to any particular node. So it doesn't have all the extra edges in some sense, the ones that add longer paths. It's just the shortest paths. Now, this is a general concept that's going to be used in a lot of algorithms we'll talk about. This one, in this implementation, we use distances and back pointers to keep track of this. But you could implement this in a lot of different ways and to take this information and reconstruct the path. So for example, this shortest path tree is going to have all the answers for the shortest path problem starting from A. So for example, what if you want to find the shortest path from A to D? Well, you just look in that dist2 map we just made, you find the key D, and then you say, oh, it was 2, right? Because we computed that already. Now, what if you want to find the shortest path? Well, it's a little bit trickier, but you can do it. You could just store or kind of start at D and figure out, okay, what edge do I take to get there? What edge do I take to get there? And so on. You can reconstruct the path from this information. That's a very common type of thing that we do in a lot of these algorithms, which is we store a lot of extra information and then we just say, oh, reconstruct the answer. There's actually a very common type of programming that we're not using here called dynamic programming, where that's a very common thing. You just say, oh, I store back pointers and then I reconstruct the answer. And then if you're lazy, you never actually explain how to do that. You just assume that whoever is reading your code will do that for you, or will understand that for you. But that's just an aside. But you can reconstruct that. Starting with D, you figure out what edge you took from your back pointers, your edge 2 map. You say, oh, we took the edge B to D. Then I know that the last thing I visited was B. When we look up the map to edge 2 for B, we said, oh, we took A to B. So I can know that my path is going to be A to B to D. Many shortest path, or all shortest path algorithms, where you kind of explore the whole graph and create all of this information across the whole graph, are going to have this property where you can use your results to answer questions for any node in that graph. Now, in some contexts, particularly in this one, you could have stopped early. Like, once you found your node T, you could return early and say, oh, I found it, it's this path and this distance away. This isn't always going to be the case. You can't always do this, but sometimes you can. But I did want to mention this general approach of coming up with this whole shortest path tree, because this is going to be kind of one of the backbones for our next type of much harder problem to solve. So if you kind of take a recap of what we've just seen, we started with the, just like everything with graphs where anything can be represented as a graph, almost every problem is going to be a graph problem on top of that. And BFS and DFS end up being really useful tools to solve these problems. ST connectivity, well, that's just BFS or DFS and checking if we hit that node. If we want to do that unweighted shortest path problems, we just use BFS and generate a shortest path tree, kind of keeping track of all that extra information, but with only minor modifications to the actual BFS code, and then compute some values back. Notice in this example, I didn't highlight this earlier, BFS is very important. That algorithm I just described with unweighted shortest paths would not work if we used the depth first search approach, because we had no guarantee that whenever we hit a node, it would have been the shortest path to that node. This was kind of a guarantee for us when we were using this level by level approach, going to all the ones one away and then all the ones two away. That invariant let us kind of know the answer right away. But what we're going to see is kind of a cliffhanger for when we start talking about more problems, more complex problems. For example, if you wanted to do something with shortest paths where we cared about the edge weights, like for example, what if each edge described how much time it would take to go from A to B? How might we use an algorithm like BFS to go through this graph? And we'll see that this actually becomes a very tough problem to start with if you just approach us from the lens of BFS. We really need some of these tools that we just addressed of coming up with this kind of shortest path tree, keeping track of extra information, to come up with a new algorithm to solve this problem. But this is a bit of a spoiler for what we're going to be talking about Friday with Dijkstra's algorithm. But now we've talked about a lot of different algorithms and how they relate to BFS and DFS, that we can solve a huge spread of problems already. But we'll see on Friday. We haven't solved everything, but we'll get there.